Let's move on to talking about other things that cause friction or energy losses in pipes. So we focused most of our attention on these frictional losses of the piping system from the pipes themselves, but there are other losses in the system that get classified as minor losses. Typically, I do not like the term minor losses, but that's the term that's used. And the reason that I don't like the term minor losses is that minor makes them sound small, but minor losses could add up to be more losses than the major losses themselves. I prefer the term local losses, but I'm not writing the textbook, so this is what we're going to use. And I want to take a look at this, and so the loss coefficient is K. And this is our minor loss coefficient. We'll even put this here, so that's a loss coefficient. And this is how we determine how much loss that we have in the system. And we actually calculate out K by looking at the head loss through an area over the velocity head. So in equation form, what that means is we're going to look at the pressure drop in our device minus 1/2 rho v squared. So you'll see this a lot, especially when you do the lab. There will be a pressure cap at either side of the minor device that we're looking at. You'll measure the pressure loss between the two of them. You'll be able to calculate out the velocity through there, and then you'll be able to say what the K value of that device is. So just so we know, K value is a function of two different things, and that's the geometry of the device, because depending on what's going on, that's really going to drive what changes, but also the fluid properties. So if this is made of a water as opposed to a gas, we're going to end up having different loss properties. Now, typically when you look at the textbook to find out what your K value is, it's going to be given for water, since that's the most common thing that happens that we're dealing with piping systems. So how do we incorporate this into our energy equation? Well, we're actually going to just change one term of our energy equation. We're going to take HF. And what we're going to do now is we're going to look at what we'll call H total. So the total frictional losses. And so what that's going to be is HF plus the sum of all of our minor losses. In fact, when you look at the equation for HF, the Darcy-Weisbach equation, the way that it's set up is that first term FL over D, then you multiply it by V squared over 2G. This FL over D is sometimes referred to as the major loss coefficient. And it's a dimensionless parameter. And our minor loss coefficient will also be a dimensionless parameter. So we'll be able to add those things together. So H total is going to be V squared over 2G, because that part comes out because both of our major and minor loss coefficients get multiplied by it. And then we have our major loss coefficient, which is FL over D. And then we're going to add to that the sum of all the minor Ks. And so we're going to call that H total. And we're just going to replace our energy equation with this term. So what happens if I have no minor losses in the system? I won't be using H total. I can just use HF. But as you can see, this part right here is still just HF. I'm just tacking on the sum of the minor Ks. Now, the K values are specific to the valve or the device, and different manufacturers will have different values. The values in your book are an average, and if you look at those tables, they have a error of up to 50%, but it's pretty good for what we're doing. So if we take a look at it, let's look at some minor losses here, and we have to think about what's going on. So what causes minor losses? Pipe entrances and exits. So as you are coming from, say, we've got a situation where we've got the big tank, and then we have that exit coming in there. Well, we're going to have a loss of that entrance because that fluid has to move around. Typically, if it's a sharp-edged entrance, it's 0.5. If it has chamfers or radii, it'll change a little bit. And an exit's just that. Pipe ends, and we have fluid flowing out of it. Exits are always 1. Makes it nice and easy. Sudden expansion contraction. So if we have a pipe that immediately goes from like 1 inch and steps up to 3 inch, well, we have mucking around with the kinetic energy because we have this region here where it's going to pull the fluid back. And if we have a contraction, we get the same thing because we've got fluid hitting up here. It's got to mosey its way around there. Bends, elbows, tees, other fittings, those kind of things will mess around with the kinetic energy. Valves obviously will, depending on how they're put together. And gradual expansion and contractions, even though they're a lot gentler and they do, oh, look at that, kind of just easily take it, you still have kinetic energy loss through there, and you have to account for that. So I want you to take a moment here, and I want you to look at these cross-sectional diagrams of different kind of valves. Now, if we're looking at a 1/2 inch pipe, which one of these do you think will have the highest loss factor associated with it? Who's going to have the highest K value? And I want you to think about something. K value basically is all based on how we're messing around with the kinetic energy in the system, because that's what's going to cause the pressure drop. So which one of these do you think is going to give you the greatest K value? I'll give you a few moments to look at that. If you want to pause the video here, you can do that. Okay, ready? 3, 2, 1. So there are the K values for a 1/2 inch pipe. And as we can see, the globe valve has the highest one. And so if I look at that, well, it's like my fluid's got to make that S pattern through there, so that's kind of a pain. I mean, the angle valve's got a lot going on too, because you got to switch through that, but the globe valve's the one that's going to cause you the most trouble. So how do I go and figure out what my K values are? Your textbook has tons of charts and tables that will have the values on there. So a lot of the fittings and stuff will be tabulated. That makes it pretty easy. But we do have some charts we have to look through. So here we go. Here's a couple different kinds of entrances. So we have the emergent entrance here, which is this kind of sticking out in the pipe. Here's ones for just a regular entrance. And see right here, sharp edge, 0.5. Probably the more common one that we'll end up using. But you can look at it. It's like, okay, if I got a chamfer in there, how do I figure out what the loss factor coming in is? And so you just look at the pictures and you go, okay, R over D. You calculate your radius over the diameter of the pipe, find out where you're at. You look at your ratios here. So here's R over D line. You just come up, you read over what the K value is. Chamfer, we've got the same kind of thing going on. We can come over, this is the table for sudden expansion and contraction. There's actually a couple of equations that you could just, that this is plotted from. But as you can see, you can look it up on the chart. And it's all about paying attention to what's going on. Little d is a smaller diameter, big D is the bigger diameter. When you're dealing with the sudden expansion, there's little d, there's big D. Sudden contraction, there's big D, little d. So when we talk about sudden expansions and contractions, it's all based on which way the fluid's flowing. So my fluid's coming in from this direction, that would be an expansion. If it was coming the other way, it would be a contraction. So it's always based on where the fluid is flowing. This next one here, this just shows you a conical diffuser. And so if you look at it, once again, it's just you got to piece the thing together from the picture. So they're looking, you got to find the cone angle, which is, this is 2 theta. Figure out what's going on. Little d over big D, you just find the ratio there to know what line you're looking at, and then you just read up from the angle to your line, read over for the K value. This one's not in your book, but I know we do talk about HVAC systems a lot. So for a regular 90-degree bend, you can see that we have a loss value of about 1.1. And that really comes down to that fluid cannot make that 90-degree turn, so you get a low pressure region here, you get a low pressure region here, which causes the flow to turn around. And so what you can do is you can put little guide vanes in, which are just little pieces of sheet metal that have a little bit of angle to them to guide the flow through, so you're using the entire length of the duct. I mean, you still have a little dead water region here, but things are a lot better, and you can see the loss value drops down to 0.2. And so this is all that minor losses are. we just add them into our system just as we've been using them, but now that gives us that last little component of our energy equation. So we can find the major losses, add to that the minor losses, and then go about solving the equation for what we need from the piping system. Now it seems like there's a lot going on in the piping system, but if you just sit back and look at it, everything's the same as what we've done up until this point. We've just now added this new little wrinkle. And so now we're ready to go. So the next couple example problems will be full-blown piping systems where we're solving a lot of stuff.